Welcome to session 10, Math 82, folks. Today we are going to be thinking about the method of undetermined coefficients and the underlying theory that has to do with linear algebra. Make sure to go to page 5 of your notes outlines, where we start with the linear algebra review. What I would like you to do is pause the video and ask yourself, when you take this particular set of vectors, which is linearly independent, how many other equivalent statements can you think of that would tell us that that set of vectors is linearly independent? One example would be to put these vectors as columns in a matrix and then say the matrix is invertible. So that is another way to say that those vectors are linearly independent. Pause the video and see how many equivalents you can come up with. And then we will come back to when AX equals B has a unique solution. Okay, how many equivalents did you come up with? Let's see if you came up with some of the same things that I did. The following statements are equivalent. The first, just repeated here, is that the set of vectors is linearly independent. We'll use Li for the shorthand for linearly independent, so I don't have to write it out fully each time. Another way to state that this collection of vectors is linearly independent is to say that the only solution to the linear combination equation is the trivial solution, in which all three unknown coefficients that we're looking for must be 0. Another equivalent statement is to say that the matrix whose columns or rows are made up of these vectors is invertible. Another way to say this is that the matrix is full rank or has 0 nullity. Remember your rank nullity theorem that says that the rank of a matrix plus the nullity of the matrix equals the number of columns or rows of the square matrix. Another commonly used test is to look at the determinant of the matrix A, and if the columns are linearly independent, then the determinant is not going to be 0. So this concept of the matrix A being invertible or the columns of A being linearly independent is very strongly connected to the question of when the system that involves that matrix A, AX equals B, will have a unique solution. Pause the video and see how many different statements you can come up with. Okay, let's write down a number of statements and see if we came up with some of the same things. Well, first, the system has a unique solution precisely when the matrix A is invertible, because then you can pre-multiply both sides by the matrix A inverse and get the unique solution X. So A is invertible says A inverse exists. Another test for the inverse of A existing is that the determinant of A has to be non-zero. We can also say that the dimension of the column space or row space is n if A is n by n. That's another way of saying that A has full rank, or that the matrix A has n pivots. If A has full rank, then the nullity of A is 0. That's back to our rank nullity theorem. The nullity of A being 0 means that the 0 vector is the only vector that the matrix A can multiply that will send the product to 0. It's also the case that if A is invertible, A inverse exists, none of the eigenvalues of A can be 0. And as we saw above, the columns of A have to be linearly independent and the rows of A have to be linearly independent. We can also say that the columns or rows of A span Rn when we are working in real space. We can also say that the matrix A is row equivalent to the identity. And if you think about the matrix A multiplication being a linear transformation, then that says that the associated linear transformation must be 1-to-1 and onto. There are many more that we can come up with, but it is important to keep in mind that what we are moving toward is really getting our linear independence understanding woken up. Let's go to the next page. Now that we've refreshed our memories on what it means for two vectors in real space to be linearly independent, let's talk about linear independence of functions. Our definition here says that if two functions, f and g of t, are linearly dependent on some open interval, I, between a and b, remember we're looking at the real line, then there must exist constants C1 and C2 that are not both 0, such that when you take the linear combination of our functions f and g using constant C1 and C2, that linear combination is going to be 0 for all points time on the chosen interval. What this means is that two functions are linearly dependent if you can find a non-trivial way to add them together or to take a linear combination so that their sum is 0. Note that this definition actually applies to any collection of functions, any number of functions, not just two functions. Let's look at example 1. We want to answer the question, are the functions t and t squared linearly dependent or independent everywhere on the real line? How will we address this question? Let's suppose that we can find constants c1 and c2 so that when we take the linear combination of our two functions using those constants, they sum to 0. Now, the idea is that if I want to prove linear independence, then I need to show that the only such constants that will work are c1 and c2 equal 0. That is, only the trivial solution works. If I can show that only the trivial solution works, then that tells me that my functions t and t squared are linearly independent. Now, here's something interesting that I want you to think about. If it is the case that I'm looking for a C1 and C2 that makes an equation true for every value of t on the real line, then any particular value of t that I choose will have to also work. Would you agree? So let's look at specific values of t that will make our computations easier for us. In this case, if I could choose t equal 1 and t equal -1 and see what those yield when we look at our equation, that will make things come clear. Okay, at t equals 1, if it is the case that my equation c1t plus c2t squared is 0, then it must also be the case that c1 plus c2 has to equal 0. At t equal -1, if it is the case that c1t plus c2t squared is 0, then it must be the case that c1 times -1 plus c2 times 1, which is -1 squared, also has to equal 0. Given these two equations have to be true simultaneously because my equation c1t plus c2t squared equals 0 has to be true for all time t on the real line, what I see here is the only way to make this true for all t is to force c1 and c2 to be 0. Therefore, we have shown that since the only way to satisfy this equation, this linear combination of my two functions, is to force the coefficients to equal 0, that means those functions must be linearly independent. Let's see what happens if we are looking at three functions. Remember that I said that this statement, even though I stated it in the context of two functions, can extend to any number of functions. And how do we extend that? We extend that by looking at the linear combination of three functions and seeing whether or not the trivial solution to the constants is the only solution. So in this example, I am comparing the three functions sine x, sine 3x, and sine cubed x. And the question I'm asking is, are these linearly independent for every value of x on the real line? We're going to do the same thing that we did for example 1. We're going to take a linear combination of those functions and see what has to be true about the constants in that linear combination. Now, once again, we're going to use this idea that if this equation, this linear combination, has to be 0 at every point x on the real line, then it is 0 for any specific x that I choose. And I will test what happens to this equation at three different points x on the real line, which will give me three equations and three unknowns and tell me something about what the constants c1, c2, and c3 have to be. Now I'm going to choose values that are going to make it easy to do the computations. The three values of x I'm going to choose are pi over 6, pi over 3, and pi over 2. At each of those points, I'm going to have to evaluate what sine of that point is, and what sine of 3 times that point is, and what the cube of sine at that point is. So over on the right, I'm going to just write down the values of sine x and sine 3x evaluated at those points. So my equation at pi over 6 collapses to 1/2 c1 plus c2 plus 1/8 c3 equals 0. My equation at x equals pi over 3 collapses to root 3 over 2 c1 plus root 3 times 3 over 8 c3 equals 0. And at x equals pi over 2, my equation collapses to c1 minus c2 plus c3 equals 0. I now have three equations and three unknowns, which I can simply solve for using essentially row reduction. If I take rows 1 plus row 3, that gives me 3/2 C1 plus 9/2 C2 equals 0. If I take that equation and divide through by 3, that yields 1/2 C1 plus 3/2 C2 equals 0. And if I take that equation and multiply through by the square root of 3, I get root 3 over 2 C1 plus 3 root 3 over 2 C2 equals 0. But look what we've done. We've shown that row 2 is in fact a linear combination of rows 1 and row 3. Since there are several combinations of these constants that can actually work, we can just choose one combination and see what that tells us. I'm going to insert a blank page just to show you what happens with one particular set of constants. Okay, so remember, we were searching for a combination of constants C1, C2, and C3 so that we could get C1 sine x plus C2 sine 3x plus C3 sine cubed x equals 0. And we came up with a system of equations that all had to be true simultaneously. We have been able to show that the second equation can be achieved by taking a linear combination of the first and third equations. Since the system is underdetermined, we can simply choose a set that is going to work. If we choose C1 equals -3, this immediately sets what C2 and C3 have to be. C2 is going to have to be 1, and C3 is going to have to be 4. When I plug those back into my constraint equation, what that gives me is the following. We could have picked other points x to get to this same conclusion, but the key is that we have shown that these three functions are linearly dependent. One other fun thing I would like to note is that what we have also come up with here is a known trigonometric identity. So with this example, we have been able to show that this set of functions is linearly dependent. I'm going to go back to the previous page. So we have shown linear dependence among those three functions, but it took us a bit of time. And wouldn't it be lovely to have a simpler way to check for linear independence or dependence? That is what we're going to talk about next. On the next page, we have repeated the definition of what it means to be linearly dependent for two functions. And this is going to lead us to how to use the Wronskian to make this test of linear dependence a bit easier. Let's sketch out a process for figuring out what that is. Now, this is not a formal proof, but it gives you the idea of how we got to our conclusion. And that's why I call it a proof sketch. Let's suppose that we are given two functions, f and g, that are linearly dependent. So we know from our definition, I'm just going to scroll up here. We know from our definition of linear dependence that on some interval, there have to exist two constants that are not both 0 that allow us to take a linear combination of those functions and sum them to 0. So in this case, just repeating that, there exist non-trivial constants, C1 and C2, such that I can take a linear combination of my f and g that sum to 0 for all points t on my interval. Because I have that, I can divide through and come up with this relationship. G over f equals minus C1 over C2. Now, of course, we are assuming that the function f is not going to be 0 at any point on the interval, and that C2 is non-zero. What do we see with this relationship? The function g over f is a constant. And when you take the derivative of a constant, you get 0. Let's take the derivative of both sides. The constant side is going to end up being 0, and the derivative of a ratio is going to be fg prime minus gf prime over f squared. We've already said that the denominator f is non-zero. In order to make this relationship true, that means that the numerator has to be 0 for all points t on the interval. Does this look familiar? Here's where we can make our lives a little bit easier. Notice that fg prime minus gf prime looks exactly like the Wronskian of f and g. So what have we seen here? We started with two linearly dependent functions, and we showed that their Wronskian ends up being 0. Now, just a brief reminder of logic. If A, then B, so if f and g are linearly dependent, then the Wronskian is 0, has a contrapositive that is also true. If not B, then not A. But the converse is not necessarily true. If B, then A. So for example, if a cat, then a mammal. If it's not a mammal, it can't be a cat. That's not the same thing as saying if it's a mammal, it's a cat. So what have we proven? We've just shown that if two functions f and g are linearly dependent on some interval I, their Wronskian is necessarily 0 for all points on the interval that we are interested in. The contrapositive also has to be true. And the contrapositive says that if the Wronskian is non-zero for some point t on the interval, right? We're looking at the contrapositive. Then our functions f and g are linearly independent on that interval. But be aware that the converse is not necessarily true. So this statement is not necessarily true. It is not necessarily true that if my Wronskian is 0 for all points time on the interval, then f and g are linearly dependent. Now, in the next class, we are going to learn about Abel's theorem, and we'll come back to that. It turns out that if our functions f and g are related by being solutions to a differential equation, then we can move into if and only if territory. But right now, if you just give me two random functions, then I have to be very careful about the relationship between the Wronskian and linear dependence and independence. Here's a visual way to think about this. Let's think about the world of the zero Wronskian and the world of the non-zero Wronskian. So these don't overlap. Your Wronskian is either 0 or non-zero. And then let's think about the space of functions that are linearly independent and the space of functions that are linearly dependent. Where do these fit in? It turns out that if your Wronskian is non-zero, then any two functions f and g must be linearly independent. What about if your Wronskian is 0? We know that there will be some linear dependent functions f and g, but not all of them. In fact, there will be some subset of functions f and g that are linearly independent, but that have a 0 Wronskian. If this picture helps you remember the linear dependence, independence, and Wronskian relationships, then please do make use of that. When we get together again in class, there will be a very short quiz checking whether we can remember the relationship between the Wronskian and linear independence. So once again, looking at the left-hand side, if your Wronskian is 0, your two functions may or may not be linearly dependent or independent. But if your Wronskian is not 0, your two functions are definitely linearly independent. All right, that's it for now. I look forward to seeing you all in class.